right. Our next presenter is HAIMING Chung. She will be presenting TwinkleTwinkle, Interacting with Your Smart Devices by iBlink, and this is on behalf of colleagues from Hong Kong Polytechnic University, Shandong University, and the University of California, San Diego. Thank you.
Thank you so much. Hi everyone, thanks for coming. I'm HAIMING. I'm a PhD student from Hong Kong Polytechnic University, and today I'm going to introduce my work, TwinkleTwinkle, Interacting with Your Smart Devices by iBlink. And this is a joint work with my colleagues, my supervisors, Professor Lo and Professor XINYU from UCSD. So we all know that in recent years, a great variety of HCI techniques have been put forward. However, the existing interaction techniques also benefit a lot of people in various life scenarios. Limitations and inconveniences still occur to people who have difficulty speaking or have difficulty using their hands, fingers, arms, or wearing glasses, gloves, or masks. And we all know that in the past years, the changes epidemic has made to our lives. So the weakened interaction scenarios feel our interest in researching new interaction ways to enable communications between people and device beyond using hands, face, voice, and mouse. So our question is there an HCI approach that can assist people having difficulty or inconveniences communicating with their hands, face, or mouse to interact with electronic devices? And we think eyes are just a suitable organ, as they are always exposed to signal at least a part, even wearing glasses. And we think blinking is a small, quiet, and unnoticeable movement which is suitable for interaction. So existing approaches for iBlink detection usually rely on face-attached sensors or camera-based approaches. And we think the face-attached sensors are usually considered intrusive, uncomfortable, and costly. And the camera-based approaches usually restricted by the light or live set conditions. And they usually suffer from privacy concerns, power hungry issues. And as cameras are usually require a display or UI interface, so only a small number of devices will be mounted with a camera. And most importantly, we think that the existing approaches usually designed for blink detection but not for interaction needs. So our next question is how to design a non-intrusive, accessible, and portable HCI system with the help of blinking and to make the system have proper mapping widths between iBlink and commands. And here is our idea. So we let the users blink towards any pair of the co-located speaker and microphone, and our system detects blink using the reflected signal transmitted by the speaker, and we use the rhythm-based iBlink pattern as commands for interaction. In specific, we let blink once as number 1, continuously blink twice as number 2, and 3 consecutive blinks as number 3. And we use the 1 to 3 number combinations as patterns and map them with self-defined commands or the number-based language systems like Morse code or ASCII code. And in this way, we can extend the 2 modalities of iBlink, open and close, to a variety of patterns and commands for interaction. And the reason why we use acoustic signals are listed here. We think acoustic signals can well make up for the shortcomings of cameras and other sensors. So in order to realize our idea, we will encounter several challenges. And the first one is to detect the tiny and aperiodic iBlink motions. And the second one is separating blink patterns from various interferences. And the third one is map blink patterns to self-defined commands, which is different to the previous classification-based systems whose patterns will be restricted in the predefined categories. So first, we employ the FMCW signal, and we have a phase difference-based approach to depict the iBlink trajectory profiles. And here, 2 phase points correspond to 1 blink trajectory. And to deal with different kinds of interferences, what makes our system different from other acoustic mobile systems is there is no need to remove the static interferences, as the displacement of iBlink is too small to exceed the quarter of our ultrasound signal. So the phase change of combined signals and blink induced dynamic components share the same trends as long as the repeated phase variation does not exactly pass through the 2 tangent points B and E. And next, we have to say how to select candidate trajectories with fewer noises. And the insight behind is to find phase points on the phase periods with fewer noises. And our strategies is to select the phase pairs with to find the blink trajectories with high similarities, and to compare the simulated phase without noise with the empirical phases to choose the phase pairs not fall into the black rectangles. And next, we have to segment and differentiate blink pattern on one trajectory. So we let one user blink while staying as still as possible, and we found the blink trajectory really clear. And if we let 3 users blink in random number combinations, we will find very mass blink trajectories. And we conclude the problem as the diversity of both blinks and interferences between people and between each attempt. And to focus on this problem, we inspired by the way Android and iOS design their adaptive user interfaces by setting relative constraints. So here, following this insight, we first do a code segmentation, and followed by a fine-grained segmentation, and we distinguish number of blinks using the direction. And finally, we add overproving correction parts to get the pattern on one trajectory. And then we will have a vote-based method to select the most frequent pattern as the final pattern. And we implement our system following the shown codes and poses. We also did extensive experiments with different settings in different impact factors, always very good results. And our system also show good feasibilities in terms of different font sizes and real-life scenarios when people wearing glasses, hats, or masks. And we also did some user study related to HCI issues with all encouraging and good feedbacks. Here is the conclusion of our work. So on the technical base, we first use phase difference of acoustic FM CW signal to sense aperiodic subtle motions such as blink in a contact-free and training-free way. And on interaction base, we design a new HCI method. First demonstrates the feasibility of perceiving controlled and rhythmic eye blinking and map them with number of combinations for interaction. And on the system base, we implement our prototype on smartphones with very high precision and generate well across users and environments. Thank you. And any questions or comments? Thank you.
Going to. Can you talk about how easily the participants in your studies were able to learn the patterns that you were testing at the end of the study?
Well, actually, in our system, we can let the user design the pattern as they like. So blink, another number combinations will be okay. So it's very easy for the patterns to participate in our experiments. Thank you so much.
All right, our next presenter is